Okay, so it's a great pleasure to have Ben Williams from the University of British Columbia. And also, thank you very much for starting your day early for this talk. We appreciate it. So he's going to tell us about the A1 homotopy groups of GLN and the conjecture of Suslin. Okay.
Thanks, Jihan. Thank you also very much for the invitation to speak. I'm delighted to be here. At the outset, let me say that, well, first of all, can everyone hear me okay? You've got good audio?
Yes. Yeah.
Good. What I'm going to talk about is joint work with Aravind Asok. Let me fix my handwriting a bit. And Jean Fasel. And also a disclaimer, which is that I don't know much more about this than I'm saying. So if there are questions at the end, there's a good chance I won't know the answer. Let me begin with the following. Quillen defined K-theory in multiple ways, and one of the definitions by Quillen of the algebraic K-theory of, say, a field is that it's the homotopy groups of a space, the classifying space of GLK, but that's a K by 1, so that's not the right answer. So with the plus construction applied. And this definition makes sense when I is at least 1, and I will say that these groups here, these are still somewhat mysterious or hard to calculate. And what does this plus construction do? Well, the plus construction has two properties of note here. One is that, oh dear, I don't mean N there. The homology of the plus construction does not change the, well, the plus construction preserves the homology of the space in question. And second, pi1 of BGLK maps to pi1 of BGLK plus, and this is an abelianization. Using this presentation of K-theory, Suslin in 1984 to find, well, he did some calculations for the homology of BGLN, and that had implications for K-theories. And I'll tell you what the homology calculations were first. The homology of nth homology of BGLN of K. So this is the group homology of the general linear group of the field, mapping like this. He showed that there's an isomorphism. Whoops, something's wrong here. It should be an N. Beg your pardon. So this is a statement that says that the homology of the general linear group of the field stabilizes at N, or the homology of GLN stabilizes at N. And because the homology is not changed by doing a plus construction, I can throw in a plus here without changing the calculation at all. And second, in the boundary case, Suslin tells us how the stabilization happens in some sense. which is that there's a map from BGLN minus 1 of K. And again, I'll throw in an unnecessary plus to HN of BGLN of K. And the quotient here, the cofiber, co-kernel, is the Milnor K-theory of the field in question. And let me remind you, the Milnor K-theory of a field is a graded ring. And what we have above is the nth graded piece. And it's generated quite explicitly by symbols A, where A is in the group of units of the field, and the degree of this symbol is 1. And there's one important relation, the Steinberg relation, which is this product is 0, provided A is not 1. If A was 1, it wouldn't make sense. And the Milnor K-theory had been defined by Milner in a sort of ad hoc way to explain low-dimensional K-theory, K0, K1, and K2 of the field. And here we are seeing it show up coming from quite natural considerations of objects you might think are important, the classifying spaces of the general linear group over a field. With this theory above, Suslin defined a Hurewicz map. As follows: you go from Quillen's K-theory, which is a homotopy group of a plus construction. And then you go to the homology group. This is the Hurewicz map from that we know and love. And then Suslin's work says that this stable homology group here actually agrees with a very specific unstable, in the sense of the general linear group stabilization, homology stabilization group that we have here. That's this is an isomorphism. And above here, we have this quotient map. So there's a map from HN, BGL, and K plus to the Milner K-theory. So in the composite, we get a map from Quillen's K-theory to Milner's K-theory in degree n. And I will call this map Sn and refer to it as Suslin's Hurewicz map. And this is the unexpected comparison between, or an unexpected comparison between Milner and Quillen K-theory. What's expected is this. This is there is a comparison that you might expect, sort of built into the theory, from the K-Milner ring to the K-theory ring of Quillen. This is because the source here is given very explicitly in generators and relations, and those generators map to to elements in the target, and the relations map to relations between them. Explicitly because K Milner 1 of K maps isomorphically to K Quillen 1 of K, and K Milner 2 of K maps isomorphically to K Quillen 2 of K. This breaks down, by the way, for higher degrees, but because you have this this map in degrees 1 and 2, you get a map of rings as indicated. And here's something that Suslin proved. It's just great piece of mathematics. The composite K Milner and K to K Quillen and K back to K Milner. This is the part using this comparison, the Hurewicz map. This composite is multiplication by n minus 1 factorial. And I'm going to call this a conjecture. Suslin referred to it as a problem. The image of this map, Sn, is not any bigger than what's forced by the observations above. And immediately after articulating this, Suslin observes that it's known when n is 1 and 2, in which case it comes from classical stuff about low-dimensional or low-degree algebraic K-theory. And it's also true when n is 3, where it's slightly deeper. And there the matter rested for a while until some time ago we were able to prove that it's also true for 5. It's not known for 4 or anything bigger than 5 at present. And my idea is to reconstruct a map like Sn using A1 homotopy. And here we will assume that K is perfect, infinite, and of characteristic different from 2 and 3. So I feel obliged to say some things about A1 homotopy theory, not too much, but some. We'll be working with varieties and more generally, perhaps schemes. And whenever such a thing arises, a variety or scheme will be, I'll view it using the functor of points formalism throughout. So if X is a variety, then I'll really think of X as a functor on rings, essentially. And X evaluated at a ring R is defined to be the set of maps in the category of K schemes. Everything will be over the field K. Maps from the spec of R to X. And this is particularly well suited to the sorts of objects I'll be considering. For instance, GLN is a variety. It's a group scheme. And this theory calls for a definition of GLN of R, and that is exactly what you think it is. It's the set of matrices A of that size such that A inverse exists. And there are a number of other varieties that that will show up. The special linear group, the symplectic group may make an appearance affine n space over K. And in this case, affine n space over K, when evaluated at a ring R, gives you R to the n. This is flat n-dimensional space. Here's one that will also show up, affine n space minus the origin. This is a motivic sphere, but when you evaluate it at R, what you get is the set of unimodular rows of length n in R. That is to say, vectors of length n in R, or n tuples of elements in R that generate the unit ideal. And I want to define a kind of Stiefel variety. Now, this isn't the usual definition of a Stiefel variety, but I'm going to call it a Stiefel variety anyway. By the following rule, or I'll tell you what the R points are. At any rate, the R points of this thing are the set are made up by the set of pairs A and B, where they're both I by n matrices, and they have the property that A transpose times B is the identity. So here, either A or B, let's say A is an I by n matrix of rank I. So it's a maximal rank, not potentially non-square matrix. But then the R points here carry around a sort of a complementary matrix B as well. These objects, these varieties, are all being viewed as functors X from the category of smooth affine K schemes, and take the opposite category of that. I mean, this is really a subcategory of the category of rings over K. So I'm just using fancy language here. To the category of sets. So this is how I want to think about varieties. They are functors from a category that is really a category of rings to the category of sets. And to do A1 homotopy theory, I'm going to use a simplicial model category. And to shoehorn, well, to get simplicial structure in here, objects are functors now from the category of smooth affine K schemes up to simplicial sets. And I'm giving myself a simplicial direction here, and varieties are included among these objects. By, well, to evaluate X at some affine scheme, I evaluate X at R, and this is originally a set, so now I view this as a simplicial set concentrated in degree 0. The major virtue for the present talk of allowing the simplicial direction is that I can talk about BGLN. We can now form BGLN. BGLN is a functor that takes in a ring R and produces a simplicial set, which in this case is the almost tautologous BGLN evaluated at R is B of GLN of R. That's perhaps parenthetical. I said there was going to be a model structure. I'm not going to go into all the details of that, but two kinds of map are declared to be equivalences. There's a, first of all, the projection from U cross A1 to U. That's an equivalence in the A1 homotopy theory. That's what gives it its name. And there's another kind of map that's an equivalence, which is best articulated this way. If, well, this is not the full story, I'm sorry to say, but it'll do for present purposes. If U and V are a Zariski cover, now the true story is the Nisnevich topology is used, but I'm not going to worry about that. If U and V are a Zariski cover of a variety, so that is to say they're two open sets that cover the variety, then I need to legislate to say that this is a homotopy pushout. And the two kinds of equivalences mentioned above there, they combine to give you a statement like the following. If F from Y to X is a map of varieties that locally, in the Zariski topology, it locally resembles U cross AN projected down to U, then F is an A1 equivalence. And here's an example that's important to us. If I take this particular Stiefel variety that I defined earlier, which will, the R points here consist of pairs A and B, but they are 1 by n matrices. And they have the property that really essentially the dot product here, A dot B, is 1. I can map that to the affine n space minus the origin, where the R points are just unimodular rows, and the morphism here is for getting B. And this map looks locally like it's of this form. It's technically a torsor under a vector bundle. So this map here is an A1 equivalence. I did say something there that I'd like to draw your attention to. This sort of object on the right is called, or it's known as, motivic sphere. Specifically, this thing is the n-1 plus n alpha sphere, or in other notation, because we need to have lots of different notations for things apparently. S2n-1 comma n. From the A1 homotopy theory, I will need also to know that there are, under certain circumstances, A1 homotopy fiber sequences, but I won't go into the details. And second, there are A1 homotopy groups, but they are actually group sheaves. These are, strictly speaking, sheaves on the big Nisnevich site. Of smooth K schemes. What do you need to know? You need to know this. If I have pointed object X, I'll suppress base points. I can take the ith A1 homotopy group object of that, and that's a sheaf, so it only really makes sense after or becomes a group after evaluation at something. And as a rule, I will evaluate at fields only, because the theory is essentially regulated by what happens at fields. And this will be, or this is a sheaf of abelian groups. Now, the definition of this in general is involved, and I want to avoid giving it. And what I will say is that sometimes pi I a1 of x f admits a more elementary description. Let me define an algebraic n simplex. This is well, it can be explicitly given as spec of something. And abstractly, it's isomorphic to affine space, so it's just flat. But if you've ever tried to define the simplices in ordinary topology, this equation should appear familiar. It's the usual way of defining simplices in ordinary topology is to use this equation and then some inequality constraints on the xi's. We don't have the inequality, so we just use this equation. And we can assemble these simplicial, or these simplices together to produce a cosimplicial object. This is a cosimplicial variety. And I will define the singular A1, or the A1 singular construction of X. Well, at R, that's a simplicial set, and I want to take the n simplices, and I will define this to be X evaluated at R cross delta n alg. And so I'm taking a diagonal of a bisimplicial construction in here somewhere. But the fact that there's a cosimplicial structure here means that these objects that I'm defining, they do assemble together to give a simplicial set, and we obtain a functor sing A1 X. So if you start with the sort of object that I'm considering, a functor to simplicial sets, then this sing A1 produces another functor of the same kind. And there is a natural transformation. X to sing A1 of X. And this A1 singular construction is part of, well, from the model category point of view, this is part of a fibrant replacement functor. And occasionally it's enough so that sometimes, and the work here is by Asok, Oiwa, and Vent. Pi I A1 of X, when evaluated at a field F, sometimes this turns out to be just equal to pi I of sing A1 of X evaluated at F. And the thing on the right here, this thing has the virtue of being a simplicial set. So it's not, there's no A1 homotopy theory on the right. And F is a field. And that sometimes is a weasel word, of course, when. I'm not going to specify, but it will be the case whenever I want to calculate a homotopy group in this talk. Okay, so I said I wanted to produce Suslin's construction, or Suslin's map again, and let me get on that. I'm going to start with BGLNF. And over here, oh, dear me, I'll have Sing A1 of BGLNF. Oh, and by the way, the homotopy groups of the Sing A1 of BGLF, those have been considered long ago. That's Karoubi VMIOR K-theory is what that is. So it predates the modern A1 homotopy theory by probably 20 to 30 years. And the Karoubi VMIOR K-theory agrees with Quillen's K-theory in, well, when the ring in question is, say, non-singular. So there is of course, there's a natural transformation across here, and that factors, and it factors. So this is going to calculate, I should make a note about that. This should, related to that Karoubi VMIOR K-theory story, pi I of this recovers Quillen K-theory. This is when I is between 0 and n minus 1. And in particular, if n is at least 3, the fundamental group here is abelian, and the plus construction has a sort of universal property. So this will factor like this. Here's a factorization of the natural transformation through the plus construction of BGLNF. Okay. And there is a commutative diagram. So I'm going to have n plus 1 BGLNF plus. I'm making a slightly peculiar choice of what indexing to, or what indexes to have here. Why do I have n and n plus 2? Maybe that'll become clear later. So the homology here, the n plus first homology of BGLN plus 2, this is the same as the case of n plus 1 here. I could replace it by n plus 1. And the quotient here is what Suslin calculated. It's K Milner n plus 1 of F. So we have that much. And I can map down here to the singular construction. And those are homology groups of simplicial sets. So I can compare with the homotopy groups, but the homotopy groups of the singular construction in this case recovers for me the A1 homotopy group. And there's a few things to note. The object that goes in this spot here in the bottom right, well, there's a theory of fiber sequences, and what we're looking at in the bottom row is the homotopy groups of a fiber sequence. And down here we should have pi n A1 of GLN plus 2 modulo GLN, and that, because of the way I set up my Stiefel variety, is that quotient is pi n A1 of the Stiefel variety I had earlier, n plus 2. And some facts are known. These are due to Morel, really, of about pi I A1 of the Stiefel variety. this vanishes when I is less than n. And the first non-vanishing one, that's due to Morel. And then the first non-vanishing one, I learned this from Jean Fasel. When I is equal to n, we get a sheafified version of the Milnor K-theory when n is odd. And we get the Milner-Witt K-theory when n is even. And let me postpone telling you about the Milner-Witt K-theory for a moment. I will say there is an action by pi1 a1 bgln plus 2. Well, that's just the sheafy version of k1, so it's gm on the groups and on these groups in both cases. It's trivial when n is odd, and in the other case, the quotient is k Milner n plus 1 in both cases. So I said that in a silly way. The group acts in both cases. It's trivial in one case, so the quotient is the group, and in the other case, it's not trivial, and the quotient is, the effect of the quotient is to get rid of this w that I hadn't explained. So it's Milner K-theory in both cases. Okay, let me go back to this huge this commutative diagram I hadn't finished writing in. So here we're going to have either K Milner or K Milner-Witt, as the case may be. And there is a relative Hurewicz map, or a relative Hurewicz theorem, that says that the first relative homotopy group, the homotopy of the fiber, can be mapped to the first relative homology group, and the effect is to mod out by pi1 the pi1 action of this space, so that in all cases we end up with Milner K-theory here. And I'm missing an F, but let's put it there. And this is an equality. So this is a relative Hurewicz map. Well, a map that we can analyze using the relative Hurewicz theorem. Okay. And that, well, that justifies, I think, the following. We define Sn plus 1 with the bar to be the map from above, going from pi n a1 of bgln plus 2 to pi n a1 of the Stiefel variety v2 an plus 2. So that's simply the map from here to here. And why do I think that's justified? Well, the Karoubi VMI K-theory tells us that this is the source of this map is Quillen's Kn plus 1. And the target here is either the Milner or the Milner-Witt K-theory based on the parity of n. So Sn plus 1 goes from Quillen K-theory to Milner or Milner-Witt K-theory, as the case may be. And it's this arrow here. And it quite clearly admits a comparison to what is Suslin's map. This is Sn, as to n plus 1 as defined by Suslin. Okay, so I would like to say something about Sn+1, this map, given the new technology. And to do that, I will look at the homotopy long exact sequence of, well, you take GLN, map it to GLN plus 2. The quotient is this Stiefel variety. And in a certain range, this will take this form, pi n plus, all my homotopy groups from now on, unless otherwise stated, are A1 homotopy groups, and I will drop the A1. So we have pi n plus 1 of BGLN plus 2, and pi n of V2 AN plus 1, mapping to pi n BGLN, mapping to pi n BGLN plus 2, and then you would get to pi n minus 1 of the Stiefel variety, but that's 0. So the sequence ends with a 0 there. This group here is ordinary Quillen K-theory. And here we have either Milner or Milner-Witt K-theory. And here we have a mystery group pi n BGLN. And here we have Quillen K-theory. Again, just writing in names for these things. And then that maps to 0. Oh, and this is the map that I called S bar n plus 1. Let me remark, pi I of BGLN is isomorphic to pi I of infinite BGL, which is the Quillen K-theory. This is if I is less than n. So that this group here, this is the first unstable group. The homotopy groups of the BGLs, they stabilize, and that highlighted group is right on the boundary. Incidentally, this explains why I have n plus 2 here rather than the more natural n plus 1. Why did I choose n plus 2 and n rather than n plus 1 and n? The reason is that I get the first unstable group here, but I'm still in the stable range for this group over here. So I'm prepared to make a conjecture. The above yields a short exact sequence. Zero to k Milner, possibly Witt, depending on the parity of n plus 1, modulo n factorial, pi n BGLN to k Quillen n to 0. So this is a presentation of the first unstable A1 homotopy group of BGLN. And this conjecture is known when n is 0, 1, or 2, and not otherwise. And I think this is an important question. It does have this connection to the problem of Suslin, and it also is important in its own right because of what it tells you about, well, the general linear group in A1 homotopy theory. So what about the case where n is 3? Well, this relates to the map S4. This is Suslin's conjecture in the case of n equals, or the case of 4. Well, about this, I can say a few things. I can't establish the conjecture, unfortunately, but I can get somewhere. Pi3 of BGL3 is isomorphic to Pi2 of GL3. And that's isomorphic to, there's no harm in replacing GL by SL. Pi2 of SL3. And we can take a detour through stable A1 homotopic theory. And this is stable in the sense of spectra. In fact, P1 or bispectra. There is a motivic Hopf map. You take affine 2 space punctured at the origin. P1 is a quotient of that. And each of these, both source and target, they're both motivic spheres. The source here is the 1 plus 2 alpha. Sorry, bungled that. This is the 1 plus 2 alpha sphere, or the S32 sphere. And the target here is the 1 plus 1 alpha, or the 2-1 sphere. And there's a you can construct an isomorphism from Pi3 of the suspension of SL3 to Pi2 of the cone on eta. And so there's an isomorphism I think, am I off here by, sorry. Yes, no, I'm fine. Stable here means the stable in the sense of spectra. So there's a comparison from here to here. The stable homotopy groups of SL3 are, this stable homotopy group of SL3 is isomorphic to Pi1 stable of the cone on eta. And the stable homotopy groups of the cone on eta, those are that's the sort of thing that the people who think about stable A1 homotopy theory can tell you very quickly. And this was communicated to me personally by Oliver Rundigs, who showed that there is an inclusion K Milner 4 mod 12 to this Pi1 of the cone on eta, and that's a stable group, so I'll just write S there. And as a corollary of that calculation, we get a commutative diagram. K Milner 4 mod 6 mapping to Pi3 BGL3. This much, we know that this map exists, but we don't know that it's an inclusion, and we'd love to know that it's an inclusion. That's essentially the conjecture I made. And we can map this down to the stable homotopy group, Pi3 stable BGL3. And then the lemma above says that this includes here, which is good. It's not perfect, but it's good. So we can deduce that there exists an exact sequence 0 to X to K Milner 4 mod 6 to Pi3 BGL3 to K Quillen 3 to 0, where X is 2 torsion. And the conjecture is that X is 0, but what you get is 2 torsion. So there's that. That's the best I can do for n equals 3. And then for n equals 4, the answer is, it looks perhaps less satisfactory, but it's really more, it's better, I think. Because in n equals 4, what we have is not enough to establish the conjecture I made here. about the homotopic group of BGLN, but it is enough to establish Suslin's conjecture. And when n equals 4, the idea is to exploit some accidental isomorphisms of low-dimensional Lie groups. GL4 to GL6 to V2A6, that's the fiber sequence we're trying to understand. And we turn that, well, you can turn it into SL4, SL6, V2A6 without much difficulties. And then, or that doesn't change the calculations at all, really. Instead of studying that, I'm going to mod out by the symplectic group that sits inside each of SL4 and SL6. So I'm going to compare the map of GL4 to GL6 with this map from SL4 mod SP4 to SL6 mod SP6. So I mod out by the symplectic group. And this seems to give rise to, well, a miracle happens here, and it's very particular to this case. So it doesn't seem to generalize. We get SL4 mod SP4. Well, that happens to be A1 equivalent to SL3 mod SL2, and that happens to be A1 equivalent to A3 minus the origin, which is the sphere. That's the 5-3 sphere. SL6 mod SP6, no miracle really happens for that, but this object has a name, a symbol associated to it, which is X3. And the upshot of this is that there is a comparison of the original sequence GL4 to GL6 to V2A6 that you would like to study, or I would like to study. There's a comparison of that with the sequence A3 minus the origin, which is a sphere, to X3, which isn't, but is something that people have looked at, and then to A5 minus the origin. That happens to be the third space. And two of the objects here are spheres. And so to study pi3 of GL4, we should study pi3 of A3 minus the origin, and that is a sphere. So again, we turn to the stable A1 homotopy theory, and now I can use a published theorem. This is due to Oliver Rundigs again, joined with Spitzweg and Östvar. They tell us, among other things, that there exists a short exact sequence from 0 to K Milner 5 mod 24, pi3, and this is not how they would write it, of course, because they're doing the stable homotopy groups, but this is the stable group that fits in here. And then to, oh dear, I think I've left something out in my notes. Let's write pi3 of x3. Let's just treat this as a mystery for the time being. But the key thing is that there's an inclusion here of K Milner 5 mod 24 into the group that we're comparing with a pi3 of GL4. And there is no Freudenthal suspension theorem for A1 homotopy theory. So the following deduction is non-trivial. We published this year. We said that there exists a short exact sequence where the only difference is the omission of the word stable. So this is a calculation of an unstable A1 homotopy group of a sphere. So that's great. And that actually is enough to settle Suslin's original question in the case n equals 5. But that's not really where my interest is currently. There's a consequence of this for pi3 of of GL4, and it's this. There exists a short exact sequence. We have K Milner, sorry, in this case, it definitely is a Milner Vit, mod 24, mapping to pi4 of BGL4. So that's the group I'm interested in, to K Quillen 4 to 0. And this maps down to K Milner 5 mod 24 to pi3 of A3 minus the origin. There's a comparison like this. So we did obtain a short exact sequence 0 to Y to K Milner Vit 5 mod 24 to pi4 of BGL4 to K Quillen 4 to 0. And here Y is contained inside the kernel of the map that reduces Milnor Vit K-theory to just Milnor K-theory. And again, ideally, this is the conjecture, Y is 0. Okay, that's where I wanted to end. I suppose I should perhaps tell people who want to know what I mean by K Milner Vit, because I've used it a few times, but I'll stop here.
Okay, thank you very much, Ben, for the great talk. So let's see if there are any questions from the audience.
You mentioned that you get Suslin's conjecture on n equals 4. Is that the case?
For n equals 5, for this case, right?
It's 5.
Yeah, so there's a shift in the indexing. So here the general linear group that I'm looking at is GL4, and the map that the sequence is this one, K Quillen 5 to K Milner 5 pi3 A3 minus the origin pi3 x3, and that is compared to K Quillen 5 to K Milner Vit 5 to pi. There's a few ways of writing this BGL4 to K Quillen 4. And this is S5, and this is what I called S5 bar. So Suslin's conjecture is that that this is exact. K Quillen 5 to K Milner 5 to K Milner 5 mod 24. Whereas the version that's most relevant to the homotopy groups of the general linear group is the way that was phrased was K. So this is Suslin, and the indexing here is 5. When it's done for the general linear group, the way I phrased it was the 4 case, because that was K Milner Vit 5 mod 24 to pi4 BGL4 and to K Quillen 4 to 0. And the techniques I outlined, they do show this, and they don't quite show this is exact. And there's a shift in the indexing.
Thanks.
Okay, any other questions?
So some years ago, 20 years ago, I was looking at sort of the opposite question about the map, the image of the map from Quillen K-theory to Milner. I'm sorry, from Milnor K-theory to Quillen K-theory in the case of number fields. For number fields, the K5 is not there's not so much, but it was still then at least at that point it was still open exactly what the image of Milnor K4 in Quillen K4 would be for a real number field. But we had some bounds. We could show that the image was non-trivial for some, depending a little bit on things like Picard groups and Ray class groups. So I wonder, but I never actually considered this particular question. So have you? But I think some of the examples we looked at, one could then ask, okay, what is the image back in Milnor K-theory of the non-trivial image from? I mean, so for example, for the real quadratic field Q square root 7, we know that that the image from Milnor K4 to Quillen K4 is a Z mod 2. And one could check whether, the conjecture would be that the map back to Milnor K4 would be trivial. So have you checked any things like this or looked at particular, or are you most interested in generic fields?
I am mostly interested in generic fields. And this is coming from some recess of my memory. This is not fresh in my mind. It's my recollection that for number fields, this map is often just 0. This map.
Yeah, in degree 5, yes. But I was thinking of K4. You're right. I mean, in K4, the symbol -1 repeated 4 times is 0. In well, 8 to the 4th is 0. So the symbol -1 -1 -1 -1 is 0, and anything in K5 is of the form -1 -1 -1. Well, 4 copies of -1 and then some unit x. So the image of Quillen K-theory. Well, so the image of Milnor K5 and Quillen K5 is 0 for number fields.
And even in the n equals 4 case. So what I should have said is that my belief is that fairly often, perhaps always for number fields, this Suslin map is not very interesting. I think it might be 0.
I mean, the conjecture is that it would be 0. So the K4 would be an element abelian 2 group. So multiplication by 3 factorial would definitely kill it. But the question would be, but if there are classes in the Quillen K-theory that are not coming from the Milnor K-theory.
Well, the comparison map from Milner to Quillen is an edge map in the spectral sequence computing the K-theory from the motivic cohomology. The Milner K-theory is a line in the motivic cohomology, and that's the whatever page of a spectral sequence. And from that point of view, the question that you were studying is what are the differentials in the spectral sequence computing K-theory from motivic cohomology? And people are certainly actively working on that. I would hope that if we can make progress on this question, which is highly related, that would inform those calculations. But so far, I don't have any progress of that nature to report. And I certainly believe that the problem, the answer we get here, so the case n equals 5 is not interesting for number fields. And the case n equals 4, the answer that I have is up to 2 torsion, and 2 torsion for the number field is where all the action is. So this is sadly close to useless for the number field case. But I'm hoping to work on this and improve this result in particular. This is my next ambition. So I'm sorry to say I can't actually say anything about this problem.
Okay, thanks. Thank you.
Okay, any other questions for Ben? Okay, let's thank Ben again for this nice talk. Thank you very much, Ben.
Thanks for coming.